So our next speaker is Martin Petersen. With Oracle, Martin has contributed to the Linux kernel since the early 90s. As Linux storage architect at Oracle, he focuses on future I/O and storage technologies. Martin also participates in various industry standardization efforts and co-maintains the Linux SCSI stack.
All right, good morning, everyone. So I was asked to give a little bit of feedback here. I was asked to give an overview of what we're doing in Linux, and Linux from a storage perspective. And Linux is pretty big. We have thousands of developers contributing, and I don't think anybody individually is on top of what everybody else is doing. So I had to look at numbers to actually get a good idea what to talk about. And so here's a graph of the last 5 years of development activity. I'm counting commits, so the commits could be small or big. But fundamentally, you can see we have things broken up by subsystem here. We have IDE, SATA, SCSI, the core of SCSI, like basic functionality, not device drivers. NVMe, the block I/O layer, and persistent memory as a new thing. We don't really know whether it's storage or memory yet. Sometimes it's both. So we're not sure where it lands, but I included it here because there's a lot of activity going on in the area. Anyway, we have a lot of SCSI drivers. We have a lot of SCSI drivers. I mean, maybe if somebody had one, we would in theory still support an ST01 or something like that. So we have a lot of drivers. So I had to filter out all the SCSI drivers from these graphs to get a little bit of a clearer picture of what was going on. So you can see here we have the individual I/O subsystems in the kernel. IDE is our old Linux IDE stack for parallel ATA and that kind of thing. And as you can see, this is the red graph down here. There's nothing going on. It's been in maintenance mode for a while. We would really like to get rid of it. We have one maintainer that is objecting to us just throwing it away for fear of reducing and introducing regressions on his favorite legacy hardware. So it's still sitting there, but we'd really like to get rid of it. As far as SATA is concerned, you can see we're around 200 commits per year, give or take, in the SATA subsystem, sloping slightly downwards. There's not too much new stuff going on, and we'll add workarounds for devices that are misbehaving and add new PCI IDs when somebody introduces a new HCI control and that kind of thing. But fundamentally, there's not a lot of new development going on. As a matter of fact, the two only new things that have been going on in the scope of ATA are support for OPAL, encrypted drives, and support for zone drives. So I'll get back to those two later. As far as the SCSI core is concerned, you can see it's on a path that's very similar to the path NVMe is taking. And there's actually a reason for that. And that is that in Linux, unlike other operating systems where read and write operations are sort of abstracted and provided by the OS, but pretty much everything else you want to do to the storage involves a pass-through operation of some sort to cause a cache flush or something like that. In Linux, we have a pretty rich block layer arbitrating between what the applications and the file systems see and how operations are actually physically translated into something that makes sense for the hardware. So a file system can do a flush, and that will get translated into something that makes sense depending on whether it's an NVMe device or SATA or SCSI or whatever. So NVMe and SCSI are often following the same path because what we're doing is we're adding support for something in the block layer. That's the black line. We are adding a primitive, some sort of operation at the block level, and then we're implementing support for that particular feature in both NVMe and SCSI at the same time. So you can see that the block layer here has been pretty steady for a while. Over there on the left side in 2013-14, we implemented support for BlockMQ. I'm going to talk a little bit about that. That was a bit of a bump after the block layer had been a very flat line for about a decade. Nothing really was changing at the block layer between early 2000s and until we introduced BlockMQ. So things tapered off slightly, and then the last year, things have been going crazy. And I'm going to talk a little about what all that crazy stuff is. So the problem we had with the original block I/O layer, which was essentially a revised version of the way back time, like a 90s block layer, it got redesigned in the 2000s for what was modern hardware at the time. But fundamentally, the I/O path was single-threaded, and there was a big fat lock on every queue, so only one application could submit I/O to any device at any given point in time. And with the advent of PCIe flash devices, this predates NVMe slightly, but there were several proprietary PCIe flash controllers and so on, several devices that started having support for multiple submission queues. So we needed to do something pretty drastic to the I/O path to accommodate these devices. And the net result was a rewrite. Matthias, who's sitting down here, was actually instrumental in doing a lot of this work to add support for multi-queue devices. One of the benefits is that from an application perspective, the submission is lockless. Regardless of what the capabilities of the hardware is, the applications per core are submitting into a software submission queue, and then that queue then gets demultiplexed into whatever the capabilities of the hardware has. So if you have a device that only has a single submission queue, which is actually the case for a lot of devices out there, most of the SCSI controllers we have in the kernel have a single submission queue. They may support multiple completion queues through MSIX and whatnot, but the submission queue into the actual controller ASIC is single queue. But applications still get the benefit of the lockless submission. So on average, the application spends less time waiting to submit the I/O than it did in the old days when it actually had to wait for the queue lock to be free. So the new block I/O layer, block MQ, is mainly used by NVMe and SCSI. Another problem with the old I/O path is it was heavily optimized for slow media. It was optimized to reduce seeks and to merge I/Os and coalesce I/Os because devices typically had very low queue depths. So there was a win in merging adjacent I/Os together, so you would only use one I/O queue slot. The HBAs had limited queue contexts, and the devices themselves had a pretty shallow queue depth. So the core of the old block I/O stack was to try and reduce seeks and coalesce I/Os as much as possible, and we had a wide range of I/O schedulers in place that allowed us to, depending on the workload, do the right thing. Block MQ was completely in the opposite corner, in the sense that the whole point was to be lean and mean, reduce all the fat, and not have any of all this stuff in the way. The I/O path needed to be as short as possible because we've moved from a universe where all that mattered was throughput to a universe where latency really is the only thing that applications care about. You know, it doesn't matter how long time it takes to write the whole thing as long as the response is really quick. So block MQ was designed to be lean and mean and not have all the baggage that was in the old I/O path. But as it turned out, we do have applications and use cases where some of that fat from the old I/O path is actually useful. So all this flurry of activity we see here is not actually new stuff. All that stuff there, most of it anyway, is us trying to kill the old legacy I/O path completely, but move all the functionality over to block MQ that we have use cases for. And so it's really just a lot of internal shuffling and plumbing and stuff going on. And so one of the major events the last 6 months or so is that we now have I/O scheduling capability in the multi-queue path. And people are going, why on earth would you want to do that? Well, there are use cases where you actually have multiple applications running on the same system using the same drive, and you need to have some way of preventing the noisy neighbor problem, to introduce fairness and that kind of thing. And that's where the Kyber I/O scheduler comes in. That's designed specifically for that use case where you want to introduce fairness between different applications running on the same system. So it took a lot of plumbing changes to make sure that we could plug an I/O scheduler into the block M queue because it wasn't designed to accommodate I/O schedulers. The whole point was to avoid them. The default is still not to have an I/O scheduler in block M queue. You have to opt in to select Kyber or BFQ. The default is not to do any I/O scheduling whatsoever, because that's usually the best thing for your individual NVMe drives. The other scheduler option that we merged is BFQ, budget fair queuing. It's an I/O scheduler that's sort of a retake of the CFQ scheduler we had in the legacy I/O path. It's a very tunable scheduler, and it's designed for interactive workloads mainly. So think your desktop where you don't want your mouse movement to be jerky or your MP3 skipping while you're compiling the kernel, that kind of thing. So it's a very tunable scheduler, and it's probably a good fit if you have a budget laptop with a slow NVMe drive and that kind of thing, because it allows you to give good priority to the applications where you care about real-time response. Another new and exciting thing that has happened recently is support for polling. So when you have applications that are really, really sensitive to latency variations, sometimes context switches are extremely expensive, and sometimes it's just not worth it to send the I/O, do a context switch, wait for the interrupt to happen, and then signal completion. Sometimes it's better just to sit there and hammer on the CPU in a busy loop and wait for that I/O that you really care about completing in a hurry. So we added support for I/O polling, and Steven, who's down there somewhere, there he is gonna scream about that tomorrow. Oh, singing about it, even better. If you are interested in that kind of thing, I suggest to go to the session. I think it's a general session tomorrow morning. Yep. So that's really cool, and we have various ways that Steven is going to tell you about how you can decide when it's better to busy wait and when it's better to punt it, and we can do averages based on previous latencies and that kind of thing. So it's kind of neat technology. And as I said, we just added support for secure encrypted drives with Opal. So those changes there are really what's happening in the block I/O stack. But those 600 commits that cost the peak there, it's really mostly housekeeping. As I alluded to, you can see that we have like this affinity between SCSI and NVMe and block I/O changes in the development activity. And I mentioned that we have this common block layer that's kind of unusual from an OS perspective. Most operating systems don't have exactly the same thing, where a lot of the core functionality is in a common layer, and then all the specifics of the transport protocol, whether it's SCSI, SAS, Fibre Channel, ATA, USB, whatever it is sort of hidden at the lower end of the stack. So we have a bunch of primitives that a lot of operating systems don't have. Several of them have a flush primitive of some sort, but we have something called discard, which is our way to deprovision a block range. And discard is translated into trim on SATA devices, deallocate on NVMe, unmap, or write same with unmap on SCSI. But from the file system and application perspective, you just call the discard ioctl or the discard call inside the kernel, and we will take care of issuing the right command for the device in question. And the benefit of having the abstraction is that if you then layer software RAID on top, or LVM, decryption, whatever you have, that translation is still working. So you can have a RAID that's spanning NVMe and SCSI and SATA drives and do a trim, and we'll actually do the right thing. So we try to build abstractions into the block layer and hide the implementation specifics inside the device drivers that are specific to the hardware and the protocols and use at the bottom of the stack. So similar to that, and this was something we've added the last 6 months or so, is write zeros. We have this primitive that you can use to clear a block range. And what the best way to clear a block range is may depend on the device you have. If it's a thin provisioned SCSI device that guarantees that you're reading zeros back after the blocks have been deallocated, maybe that's the best way to zero the block range. So instead of having to write out zeros, the device will just say, oh, you told me to zero these blocks. I guarantee you that you're going to get zeros back if you read those blocks, even though I have no actual backing for them. So that works for NVMe's and SSDs and thin provision devices and so on. And the write zeros command can be used and is used by the file systems to clear out metadata areas and so on disk. And depending on the type of hardware and the properties of the hardware, we'll do the fastest zeroing we can of those blocks. Another special thing about Linux is persistent reservations. Most applications that use persistent reservations prepare SCSI CDBs inside the application and send them out to the hardware through SCSI pass-through in the OS. In Linux, we actually implemented support for persistent reservations as first-class citizens in the I/O stack. And that means you can have an application that uses persistent reservations, and it doesn't matter to the application whether it's actually running on an NVMe device or a SCSI device or what it is. You're using the persistent reservation primitives, and the I/O stack will do the translation into the appropriate commands for the device. And something I've been working on for a while is copy in and copy out to take advantage of the copy offload features that are in some storage arrays. Hopefully this code will land for 4.15, and it'll do the same thing. An application or a file system will say, make a copy of this block range in the most efficient way you can, and then the storage can do it without having to pull all that data into the OS and back out to the storage. So we're trying to build a richer set of operations into the block layer that allows us to take advantage of the hardware capabilities at the bottom without and at the same time hiding the implementation details from the application. Another thing that's very actively being developed, and something I have been screaming about here at SDC for several years in a row, is hinting and streams. We at Oracle have a very extensive experience with hinting and streams, especially hinting as far as our products are concerned. We get really, really good results, and several of our product lines are built around the capability that the storage knows why the application is doing I/O, and that makes it much easier for the storage to make an intelligent decision about whether to cache or not cache and where to put the data placement, that kind of thing. And so some of the stuff that we have put into the kernel recently is a set of data lifetime hints. That's especially important on NAND devices where you want to co-locate things that have similar lifetime. And you will often end up, when you're writing a file, submit multiple I/Os roughly at the same time that belong to the same file, but you're constrained by the maximum I/O size of the device. So you can't submit it as one big I/O, plus the file might be fragmented, whatever, in the LBA space. But by using these hints, you can say that all these I/Os that have the same lifetime should probably go into the same bucket on the flash, and thereby reducing write amplification and making warelabeling easier. We also have hints that you can set on a per I/O basis that says this I/O is important and should be given high priority, and we plan on tying that into the I/O polling thing in the future. And we have a background hint that says this I/O is not important, it's the backup. Don't bother stealing I/O cycles from anything else. As long as it's done by tomorrow morning when we start the next one, we're good to go. And then in terms of the data lifetime hinting, it's currently implemented using the streams directives in NVMe, but the abstraction at the block layer really doesn't preclude other implementations. As a matter of fact, there are some devices out there that use the DSM flags in NVMe and SATA and SCSI to essentially provide the same capability as streams do. And so there's nothing that prevents us in the I/O stack from translating a hint about high priority or long lifetime for write data or whatever to something that can be expressed in terms of DSM hints or logical block markup descriptor indexes in SCSI. So we try to make it as abstract and generically applicable as possible. So in terms of that, so there's a lot of talks here at SDC about getting absolute maximum performance, best latency, specifically tuning. I'm looking at you, Matthias, something for one particular application workload, and that is great. And you're always going to be able to come up with a way where you can tune a particular set of hardware and applications to just completely rip at the expense of everything else. So with my maintainer hat on, I think it's cool, technology is cool, but with my maintainer hat on, I have to put something in the I/O stack that is applicable to everything from the wristwatch and the phone up to the hyperscalers. So the challenges I generally face is coming up with abstractions and concepts that work across a wide range of applications. And that may mean that you're not getting the 99.99999 percentile tail latency across the board, but if you're getting 95% performance across all types of applications, maybe we're doing the right thing. So the general approach is we try to do something that benefits everything, and at the same time, we don't prevent people that want to hand tune and hand optimize things for a custom application. They can do that. So, zone block devices. This is something I hate with a passion. I've been resisting putting it into the kernel for years. And then finally last year here at SDC, I sat down with a couple of guys and said, okay, if we're going to do this, this is how we're going to do it. And so unfortunately, they did what I told them, and so I had no choice but to merge it. So we now have support for that. And so SMR drives are absolutely horrendous from a normal application and file system perspective, because you can only append to a limited number of zones on a drive at any given time, and that is very, very unfriendly to the way POSIX I/O works and how applications expect things to be working. So the stuff we put in sort of masks the effect of the SMR drives by providing a DM zone personality that essentially takes some of the zones away from the capacity, reported capacity of the drive, and provides a simple FTL that masks the effect of the SMR drive and allows you to put a regular file system on top of it. Right now, it works kind of, sort of, for the legacy I/O path, but as I said, we're trying to obliterate that. And getting SMR to work in BlockMQ universe is slightly more complicated, because all of a sudden you can have all cores submitting I/O to the drive at the same time, and so you need somebody to sequentialize that I/O very carefully for each of those zones. So that work is ongoing. Hopefully in 4.15 we're going to get that fixed. So, on to NVMe, another area of very active development. You can see here that we merged the initial driver in 2013. The initial driver hooked straight into the top of the block I/O stack. It wasn't really a good fit for how we generally do things. And customers really wanted things that they expected to work on other block devices like SCSI and SATA to work on NVMe, like I/O statistics and being able to tune various parameters, I/O size, and so on. And the initial driver hooked into our top of the block stack into BIOS rather than requests. And it was very fast. And at the time, we didn't have BlockMQ, so it was really the only way to get better parallelism was to hook in that way. But then BlockMQ came along, and Matthias, again, did a tremendous amount of work to get the driver converted to BlockMQ, and that happened like 2015 or something like that. And so that was sort of like the second rework of the driver. And then what we should have been done. But then you can see the development activity boomed. And what happened was the third iteration of the driver happened because we had to accommodate Fabrics. So the initial driver was very monolithic in the sense that it was written to drive a PCI device using the NVMe protocol. And then NVMe over Fabrics came along, and we split the driver into a core protocol thing, akin to primary commands and block commands in SCSI, if you will, and then a PCI-specific portion that speaks the PCI queuing language, and then a separate driver for the Fabrics RDMA binding that allows you to run NVMe over Fabrics over Rocky and InfiniBand, for instance. That code went in about a year and a half ago or so, I think. And then this last year, we merged support for Fibre Channel NVMe. So that allows you to tunnel NVMe commands over a Fibre Channel fabric. And the TCP transport binding is in the pipeline. So there's been several talks at this conference about the merits of Fibre Channel versus TCP versus RDMA. And there are definitely use cases for each of those. If TCP is probably going to be a slightly further out on the fabric capacity game where you don't have strict latency requirements. And then for stuff where latency matters, you would probably deploy Fibre Channel NVMe. And then for things where you're tightly coupling things in a cluster that pretends to be one computer, maybe, the RDMA, very tight, low latency coupling is probably going to be the game. But anyway, as a result of the third rework of the NVMe driver, we're now in the position where we can support all three. There's been several proof of concepts posted of TCP transport binding, but the official NVMe Express organization spec is not done yet, so they've just been proof of concepts, and we haven't merged them. Aside from that, the driver is pretty feature complete as far as 1.2 and 1.3 of the NVMe spec. We've added a lot of support for power management as a result of a lot of laptops now featuring NVMe drives instead of SATA drives. And as a result of a lot of consumer drives as well as enterprise drives having bugs, our quirks list is rapidly growing where we're having to work around issues in this drive and that drive. Steven yesterday was super excited about how there's one driver and it works on everything. And I reject that universe. I wish it was true. but ASIC bugs exist, and we do have an extensive list of workarounds in the driver, and it's growing. At least it's one driver, but yeah. We also have support, as I mentioned earlier, for persistent reservations in NVMe now, using the common block infrastructure for the persistent reservations, and we have target support, which means you can set up a Linux box to export any block device on Linux, whether it's software RAID or whatever it is, as an NVMe target to another system over all the supported transporters. And finally, multipathing has been underway for a while. Christoph, who's roaming the hallway somewhere, has just posted a patch set that implements support. And this morning, a different company posted an alternate approach to multipathing. From a specification perspective, work is still ongoing in the NVMe Express Technical Working Group to define ANA, asymmetric namespace access. It's the ALUA thing for NVMe. So it's slightly simpler than ALUA was in SCSI. All the things that nobody ever implemented in SCSI has sort of been left by the wayside in NVMe, and it's a much simpler spec so far. So that is coming, multipathing support. And then the final topic is persistent memory. You see there was nothing for a while, and then Intel published the ACP NFIT spec, and off it went for a while, and it sort of plateaued for a little bit. Most of the core support for persistent memory is in the kernel. Thereby not saying there's not a lot of work to be done, but the plumbing is in place, and most of the efforts at this point is concerning how you handle flushes. So if you have an application that wants to manage its data structures in a way where it's guaranteed that there's not going to be any inconsistencies after a crash when the application comes back, it'll have to do cache flushes. And that interferes with the killer app that is files. Customers really like having files. We at Oracle, we have volume managers and stuff like that. You can stick into the database. People don't have to use files. And the first thing customers do is add files to that. So they can copy them and back them up and stuff like that. We have a file system that's built into the volume manager in the Oracle database that allows you to do that. People really like files. It's a good way to manage groups of data. You can assign permissions. You can assign ownership and that kind of thing. So a lot of applications, even though they might be block-based, would like to have files. And so we have this duality thing going on in the kernel where you can take an NVDIMM and you can decide whether to carve it up or whether to use it as a block device. If your application, there has been lots of concerns this week from people I've talked to about persistent memory and how you have to rewrite the universe. You can still just use it as an SSD, and if it meets your performance numbers, go right ahead. You don't have to change your application. But if your application is of such a nature that it is a benefit to you to rewrite the application so you can manage things at a cache line granularity, I tend to think of it as 64-byte sectors because I'm a block I/O guy. But if you can benefit from that, it's might be worthwhile to rewrite the application. You know, you're going to get very different latency characteristics from doing flushes at the cache line as opposed to typical 4K file system blocks. So we support both in the Linux kernel, and the little wrinkle is how do we deal with the fact that the sysadmin might be coming in from stage left and doing a copy on the file while an application has mapped that file as persistent memory. What if you move the file? All these things. So the way file systems currently work is the file systems hide all the effects of that from the application. You know, we can relocate blocks on the device. We can toggle pages read-only in memory, do copy and write. We can do all sorts of tricks in the I/O stack and the VM stack to mask the effects of that. But if an application is directly accessing the non-volatile memory and there's no second copy, there's no cache of that data, you're accessing the NVDIMM page directly, then we need to have some sort of measure in place in which an application can tell the kernel, I would like to map this, and please make sure that the metadata is stable on disk, it's immutable, nothing gets changed. If the admin is doing something that would cause problems with this mapping, you will have to have a way to signal to me that the mapping of this file has changed and I may have to re-mmap this file. So there are currently two different implementations that are competing about which one is the right approach to go about this. One is called MapSync and the other one is called MapDirect. MapSync provides some of the benefits in a very easy to implement package, but I'm not entirely convinced that it's going to solve the performance problems for the applications that truly care about this. So I don't know if Andy's here, but he's speaking after lunch, so maybe it would be a good idea if you're interested in this to hear what Andy has to say. I assume he'll be covering these two calls. So this is like globally the activity of commits, the number of commits in the Linux I/O subsystem. So SATA, SCSI, NVMe over the last 5 years or so. You see we average about 2,700 commits per year in 2013, and we're now up to about 3,500 commits in the subsystem per year. And about 1,600 of those are SCSI, which explains why I never sleep. Because that's about 35 patches per week that I have to review and merge in SCSI. And it's mostly drivers because we have so many of them. But there's a tremendous amount of activity. And so if we filter out the drivers, right, the drivers are typically written by the hardware vendors for a particular piece of hardware. But the core code, block layer and SCSI and NVMe, we're maybe 10 people that are regular contributors to the I/O stack. So we're busy. Come help us. If you have problems, feel free to contribute. We could use more hands. Okay, that's about it. Questions?
So it seemed like you were name-checking a lot of those 10 people, right, in this room.
There are definitely quite a few of them here, yeah.
You're so shy.